Okay. We'll continue the multi-machine stability analysis, and we list some steps in order to develop the swing equation of each machine, and then you can numerically solve these swing equations. So all these steps have been covered last class. So Abdullah is asking to invite him. Who was Abdullah? Abdullah Bazid. I don't know how to invite him. Let me check the other stuff. Hamad Maruf, he didn't attend. Participant. Hussein, okay, خلاص. Thank you, Hussein. Hussein, send him the link. Okay, so let us continue. All these steps have been covered, discussed last class, and this is the swing equation of each machine. طبعا you have here BE, which is function of the Y bus matrix, and this Y bus matrix will be 3 of Y bus matrices will be developed pre-fault, during fault, and post-fault. Okay, so all this has been covered. Even the I think we stopped here. You have here 3 generators, 5 bus system. You have loads here at bus number 4 and bus number 5. And what we need, and of course you have to be given the load flow data, bus data, line data, and also machine data, inertia, transient reactance, and if we have damping coefficient also will be given. So all this should be given. Okay, this is the brief. This is the load flow results. Of course, we have to carry out. What is required here is we need the swing equation of each machine during the fault period. If a 3-phase fault occurs at bus number 4, line 4-5, and at the end of the line 4-5 near to bus number 4. So, as we mentioned last class, for this system, how many swing equation should we develop? How many? Any answer?
2.
Why 2?
Because it would have been 3, but the infinite bus has no swing equation because H is equal to infinity.
So there is no change in angle, there is no change in frequency, there is no change in speed. So we don't need to develop swinging equation for this infinite bus. If we replace it by a generator similar to generator 1 and generator 2, so in this case we have to develop a swing equation for this. Okay, so let us develop the swing equation during fault. If the fault occurs at bus number 4, and determine the swing equations of each machine for the post-fault period. And the switching scenario was the three-phase fault is cleared by simultaneously opening the circuit breaker at the ends of the faulted line. So the faulted line is now removed from the system. So you have to, from the load flow Y bus matrix, you have to remove the line, and then you have to reduce, and then you have to add XD prime of the machine, and then you have the Y bus post fault condition. So we can also write the swing equation on post fault conditions. So as we mentioned earlier, the first step is to run a load flow, and we run a load flow here. These are the results of the load flow. Voltage at each bus is given, and the reactive power of generators also is calculated here. Of course, this is the slack bus, and in load flow you already at the end of the load flow you calculate the slack bus power here. Yani we have a number here which should be come from the load flow. But of course, definitely, since we will not develop a swing equation for that machine, so we don't need this B mechanical. This is B electrical at steady state, which is also equal to B mechanical 1, and this is equal to B mechanical 2. And this is, of course, if it is calculated from the load flow, so this is B mechanical 3. But this is not needed, we will not develop the swing equation for that machine. Okay, and these are the given B load and the Q load. So this is the first step. طبعا احنا we can have another step, depends on the data. If the data are given for the same base, that's fine. Otherwise, you have to do some kind of per unit quantity changes. You have to adjust the per unit quantities. So this is given for the same base, so we take all these values right away. Otherwise, you have to, if the system base is different than the machine base, you have to adjust the H, and also you have to adjust the XD prime. And we already covered this at the beginning, how to adjust H. And okay, so for each machine, we have to now calculate, and we need to, second step is to find E prime for each machine and its angle at steady state or initial angle. So what we have here, we have I1 for the machine number 1. Omar Salman, do you have a question, Omar? Omar?
No.
Do you have a question?
No.
Okay. This is I1?
No.
Okay. This is I1, which is S1 conjugate over V1 conjugate. And VT is coming from the load flow, and this is also coming from load flow. So this is known in advance, and this is calculated. So you can have the current here in per unit. I2 also S2 conjugate, and this is given there from the load flow results. This is known in advance, and this is calculated from the load flow, and this is also known in advance as a magnitude, while the angle is calculated from the load flow. So this is also per unit, I1 and I2. Having V1 and V2, you can get E1 and E2. E1 prime equal to VT1 plus JI1 x D1 prime. So you can get E1 and E2 as a magnitude and angle here. So this is delta 1, 0, and this is delta 2, 0, initial value. Of course, for the third machine, you have E prime the same as, constant, لأنه x d prime equal to 0 as we mentioned earlier. And the x d3 prime, since it is infinite bus, it is equal to 0. So E equal to V, but actually, this is just, you have it here. Okay. Delta 3 equal to 0. Of course, this is the reference that we have. So delta 1, 3 equal to delta 1 minus delta 3, which is 0. And delta 2, 3 equal to delta 2 minus delta 3, which is 0. So it is equal to delta 2. Okay. Okay. طيب. The next step is to convert the load to shunt admittances. Having V load and the Q load and the voltage at the load buses, we can convert YL4 equal to SL4 conjugate over the square of the magnitude of VL, and V times V conjugate. So in this case, you can have, this is the load number 4 conjugate over the V4 square. So you end up with this YL4, and YL5 will be calculated also in similar way. So what we will do with this YL4 and YL5? What is the next step, يا شباب? What is the next step? Should I call anyone? السر مثلا. What is the next step يا السر? السر is with us or not?
Yes, doctor, I'm here.
So what is the next step? Why do we calculate these load admittances?
Sorry, I wasn't there. I just entered the lecture.
Okay. طيب سليمان.
Yes, doctor. I think we are going to form the Y-bus matrix by including the transient reactance of the generators.
الواي باس matrix is already formed in Y bus in load flow study.
Yeah.
So you have Y bus from the load flow. So what we will do with this Y bus of the load flow? How can we incorporate the load YL4 and YL5 to Y bus of the load flow? How to do it?
By removing, I think we will include the transient reactance of the generators. Then
transient reactance will come later. transient reactance will come later. At this stage, we need to incorporate these loads into Y bus formed by load flow. Later, we will see the XD prime of the machine, how to do it. Omar Salman? Omar, do you have an answer?
Yes, doctor. Yes, I wanted to say that the YL we're going to include or argument the YL for the in the Y bus matrix, and at the same time the X is the transient reactance for the generators.
Let me ask you, Omar.
Now,
what is the dimension of this Y bus matrix?
5 by 5.
You have 5 bus, so it's 5 by 5.
Yes.
So how to incorporate these loads in this Y bus?
Yani, since the bus 3 and 4 are already eliminated.
3 and 4?
The buses 3 and 4.
Where is 3? We have 2 loads, one at bus 4 and one at bus 5. So how to incorporate these loads?
We are going to add it. We're going to add these loads in the Y bus admittance, the admittance matrix. So the corresponding elements of the bus, elements of the Y bus matrix corresponding to these particular loads.
Which entry? Which entry? You have here 5 by 5.
Yes.
So you have Y1, Y2.
So the buses corresponding to 3 and 4 are the ones, the row 3, row 4 corresponding to column 3 and 4.
And this, أنا مش عارف أنت بتجيب ال 3 منين. Why 3? We have only 4 and 5. And you still.
I mean 4 and 5. 4 and 5. Yeah.
Okay, so this is Y bus matrix.
Yes, 4 and 5. Yes.
So this is 4 and 5. And this is 4 and 5. Okay. So these are the columns, these are the rows. So how to incorporate now? How to incorporate these bus or load admittances to Y bus matrix? And should we add it to Y1 or Y41 up to Y43, Y42, Y44, Y45? So, and this is also here. How can we incorporate this load, Omar? Any answer?
Add it to 4, 5. We add it to the rows of rows 4.
This value will be added where?
It will be added to 4, 5, doctor.
The diagonal entry.
Oh,
plus 4, and this is also will be added to Y55. So this is the load admittances will be incorporated in Y bus matrix. So next step is to the augmented bus admittance matrix after including the internal machine reactance for each generator and the admittance for each load, and the system is given M per unit as. So this would be the, we also incorporate the reactance of the machines for this Y bus matrix. So this is after adding both, and then we can reduce the matrices later on to 3 by 3 by coron reduction. First, remove row and the column at bus 4, and this is during the fault, but we will start during the fault developing the swing equation during the fault. Now we have a solid fault at bus number 4, and bus number 4 is connected to the ground now. It becomes our reference, or connected to the reference now. So we will eliminate bus number 4 completely from the Y bus matrix, and you have here Y bus is 5 by 5. Bus number 4, you have fault here, and you have the fault at bus number 4. So you remove bus number 4 completely, and then you have now, after removing this bus, you have 4 by 4 matrix, and this 4 by 4 matrix will be reduced to 3 by 3 matrix by coron reduction. And you have here coron reduction to have 3 by 3 matrix during the fault, and this Y bus matrix, the transfer admittance between the three generators here at the last stage. So because node 4 is merged with the reference node during the fault period, this is of course assuming that the fault is solid fault. And if the fault is with row and impedance, but this is not valid. So if you have here fault impedance, you have to incorporate also the fault impedance here in Y44, and then you can reduce later on. In this case, the Y bus matrix will be still 5 by 5 under the fault. Now, since the fault is solid fault, well, bus number 4 becomes connected solidly to the reference. I will tell you, we can eliminate bus 4 and column 4, row 4, and then we have 4 by 4 matrix, and this by coron reduction we eliminate at bus number 5, and then there is no generator at bus number 5, so we have 3 by 3 matrix here at the end. Then reduce 4 by 4 matrix by eliminating node 5. The modified faulted bus admittance matrix is given in the unit as. So this is 3 by 3 Y bus matrix, and you have it here. This is the reduced one. So of course you can. This is Y11, Y12, Y13. Of course, a symmetric matrix, and you have here the magnitude of Y22, Y23, and so on. And this is the angle, which is theta, as given in the power equation. This is Yij and theta ij. So you have here during the fault, the electric power of each generator can be calculated as follows. It will be E1 and also will be E2. It will be E3 not needed. So BE1 equal to summation from j equal to 1 up to 3, E1 EJ, J1, 2, 3, Y1 J, cosine theta 1 J minus delta 1 J minus theta 1 J. And this is equal to 0. Wow. Why this is equal to 0? What do you think? Should we calculate, or we can directly write it down to 0? If you look at the the system configuration here, and if you have a solid fault here, how much the power from generator 1 injected to the system. What do you think? How much? You can look at it as a single machine infinite bus. And if you have a generator here and you have a fault at this bus and you have two lines or one line and you have another generator here, so the power injected here, power transfer to the system equal to 0 if the fault occurs at the bus. And this is the situation also here. And if we have a fault at this bus, there is no power transfer from generator 1. There is no power transfer from generator 1. So in this case, you can either by substituting here, if you substitute here, or you can justify why it comes to 0. If you have you have here y1 2, y1 3 equal to 0. This is from the here y1 2, y1 3. But this is equal to 0. So what we have only is y1 1, and this is the case. y1 1. How much the angle theta 1 is 90 degrees, and this is okay. So and the angle delta 1 1 is 0 definitely. The angle when you have here j equal to 1, plus 2 3 will be eliminated, and this equal to 0. So we have only j equal to 1. So j equal to 1 by e1 e1 y1 1 cosine delta 1 1. Delta 1 1 is 0. Delta 1 1 is delta 1 minus delta 1, which is 0. And we have also this angle equal to 90 degrees. So cosine 90 will be equal to 0. So you have here the three terms that we expect equal to 0. And this is can be justified. As I mentioned, there is no power transfer during the fault, since the fault occurs at the bus. Okay. We repeat this for BE2, j equal to 1 up to 3, E2, EJ, Y2J cosine delta 2J minus. So you can have this here, and then you can find the BE2. Look at BE2 here. It's very interesting here, to have this part. Now we used to have a BE equal to B max sine delta. We used to have this formula. But now we have a real part here. You have here a part, which is constant here. And you have B max sine even delta is delta minus theta or delta minus gamma. So this power equal to real part or constant part here, which is مثلا A plus B max sine delta minus gamma. Why this A comes here, appear, and also gamma? What do you think the reason for this? What is the reason for this? What is the reason for having such constant value and also delta is shifted by an angle? Gamma, any answer? Any answer؟ الشباب مش معانا ولا ايه؟ مش عارف. سعد Ahmed.
Yes, sir.
What do you think the reason for this?
I'm not sure actually, doctor.
Any clue? Ramadan.
Doctor, I guess there is a delay showing in your PC because many students they are raising their hand up and you don't see us.
And actually, I was there is no delay, nothing, but I'm moving the cursor down to check the names and يعني select from it was down, okay. Now I have Hussein at the beginning and then Ramadan after. So Hussein, let us start with Hussein.
Yes, actually, Doctor, we have reduced the Y bus matrix and removed the bus 5. I guess this is due to that reduction.
Okay, so let us hear from Ramadan.
Yes, doctor. I think it comes from the third generator, because typically we're dealing with 2 generators, but now we are dealing with 3 and more.
طيب يعني okay, so is there any other answer? Well, actually, the reason is very simple. In this form, we assume that our network is only reactance. The impedance is only reactance part. But when you have a resistance in the transmission lines, then you can see this. It is no longer pure sinusoidal as such, but you can have such a case. If you look at the line data, and even the Y bus matrix, even Y bus. And for Y bus, you have here like resistance here. So you have here a conductance. You have here a conductance. It is not pure 90 degrees. And this comes from the resistance of the transmission lines. If you look at the line data, this is the line data. So you have a resistance here. So if you have a resistance here, we expect to know the power angle equation is not pure sinusoidal, but you have this constant value, and you have also angle shifted by gamma. So this is the reason. The reason is we have resistances. We consider resistances. If you don't consider resistance, in this case, you will end up with the similar form. The corresponding swing equation of the 2 machines, خلاص انت you calculate the BE1 and the BE2, so you can write down directly the swing equation of machine number 1, omega S over 2H, B mechanical 1, which is equal to BG load flow, minus B electrical 1, which is 0. And you have, again, the acceleration, omega S over 2H, 2 multiplied by B mechanical. We have here B mechanical 2, plus this, of course, this would be here minus. So this is not B mechanical, but B mechanical minus this part. So this is the total or resultant real part here. Okay. So B mechanical 2 minus B electrical 2. So you end up with this swing equation. So if you know the fault duration and you have the time step, then you can see how many iterations that we will solve these two equations here. Okay, so this is the swing equation during the fault. We need also to develop the swing equation post-fault and post-fault conditions, where we trip the faulted line. So we will repeat this again. We will modify the Y-bus matrix of the load flow to remove line 4, 5. And then we modify the modified 5 by 5 matrix can be reduced by eliminating 4 and 5. And the modified post-fault matrix would be given as such. So you have it here, 3 by 3 matrix. And this is the post-fault network. Of course, you can calculate from this Y11, Y12, Y13, you can calculate BE1 and BE2, similar to what we have done earlier. BE1 is in summation J1 to 3, this value. So you end up with this value. Of course, we have Y13 here. We have here Y13, which is, magnitude and angle. So you end up with this BE1. And similarly, you can get the BE2. And you can write down the corresponding swing equation, acceleration of the machine number 1, omega s over 2h1 multiplied by B mechanical 1 minus B electrical 1. So this is B electrical 1. And this is also for the second machine, you have the same. B mechanical 2 minus BE2. And this is the swing equation that will be solved after the fault duration up to the final time, final simulation time. Okay. So if the simulation time is 5 seconds and the fault there is 0.1 second, in this case from 0.1 second up to 5 seconds, you are solving this swing equation. During 0.1 second, you're solving the swing equation during the fault. So this is the case. Yes, please. If you have any question.
In this second last slide, when we're checking for stability, is the operating point delta 2, or is it this net angle after? Is the operating point delta 2, or is it delta 2 minus 0.847?
لا, it is delta 2 طبعا. Delta 2 the angle of the machine. This
Okay.
This, as you mentioned, comes from the network. From the network.
Okay, so if we're trying to check the stability, is our stability limit still 90 degrees, or is it 90 plus 0.845?
لا هو لا يعني it's not neither this or that nor that. Actually, this is not a steady state stability to have 90 degrees. Okay, this is the transient stability. You have fault. So as we mentioned earlier, the angle during the fault can go beyond 90 degrees.
Okay.
Is it clear?
Yes. Yes, all right.
Nothing, 90 degrees has nothing to do here. Yeah.
It should be delta max.
Delta max could be higher than delta. And when you have the oscillation, when you solve this, you have delta 1, 0 here. And during the fault, then you can have the angle go more than 90 degrees. This could reach مثلا 120 degrees مثلا. But it will come back if the system is stable and so on. Of course, if you يعني here طبعا لأنه it is not like a single machine infinite bus where you can say in the maximum angle equal to 180 minus the delta 0. Did you still remember this?
Yes, Dr. It's clear.
For multi-machine here, the picture is different. يعني, but definitely the angle will go beyond 90 degrees.
Yes, Dr.
And the system could be still stable. If the system is unstable, maybe you have such response. Is it clear?
Yes, Dr.
Okay, Hussein, do you have a question, Hussein? Hussein Ali?
Yes, Doctor. No, I don't have a question.
Ramadan?
Yes, Doctor. I have a question about reduce admittance matrix part A.
Yes.
So basically, we remove the column 4 and row 4 first directly, right?
Yes.
And then we do the row reduction from bus 5.
We eliminate bus 4, 5. So assume that this is the matrix A, this is the matrix B, this is the matrix C, this is the matrix D.
Okay.
The Cron reduction will give you, will reduce the matrix, will be equal to A minus B, D inverse C.
So the size of matrix D is 2 by 2.
Yes, لأنك أنت eliminate 2 buses.
Okay, and then we remove 4.
خلاص أنت يعني this is the reduced matrix now. The A matrix minus B times D inverse times C. Of course, the Cron reduction can be done column and row wise or bus wise. And I don't know whether you still remember in 520, for example, when if you want to eliminate bus number 5, and then we eliminate bus number 4 later on, and sequentially, we can do this. And this is Y11. This is Y11 minus, you go forward here. This is the pivot column, and this is the pivot row, and the pivot element here. So Y11 minus 0 times 0 over this value times Y15, Y51 over Y55. So this is why we have here Y15, Y55 inverse, Y51. So this is the in matrix form. B, D inverse C. And then you can go to this element and also do the Cron reduction. You can go this way, this element minus this times this over the this one, and so on. You can do it element by element, but definitely this is the Cron reduction in general. Okay? Is it clear, Ramadan?
Yes, clear. But can you go to the next slide, Doctor?
Okay. Next slide. Yes.
Because here the step says that first remove row and column of bus 4.
Oh yes, here لأنه الفولت here is solid fault and the bus number 4 is connected to the ground now, connected to the reference. Yani, look here, we will not do this cron reduction, by the way. In step number A, in this step, we are not eliminating the two buses. We are not eliminating the two buses. Okay? And this bus now is a reference. But we remove it completely from the matrix at the beginning. Without cron reduction, without nothing. You just remove it. Is it clear?
Yes, clear. And then we remove bus number 5.
And then you remove only one bus by cron reduction. Look, bus number 5 by cron reduction. The fault here is clear. The fault here is a solid fault. This bus becomes the reference bus, the same as a reference. We eliminate bus number 4 completely. We eliminate it, you just delete it from the matrix without cron reduction. There is no cron reduction here. You just eliminate the bus. Okay, and then you have 4 by 4 matrix. This will be undergo the cron reduction to eliminate the bus number 5 with this way. So you end up with 3 by 3 here. And then on the other part, there is no fault. This is the post-fault condition. The fault is clear. So we eliminate bus 4 and 5 by cron reduction. This is in part P.
Okay, because I tried to do the same steps, but I got different matrix 3 by 3. I'll check.
That you eliminate the bus number 4?
Yes.
Completely?
Completely, yes.
And then?
And then I've done the reduction.
You do cron reduction to bus number 5.
Exactly, yes.
And you end up with the different
matrix.
Different matrix.
Slightly different.
Slightly different, maybe لأنه يعني if it is slightly يعني can be approximated, but that's fine لأنه الcalculation this is يعني from the يعني old book and maybe some of the calculation is some يعني لما this is the way it is done يعني this is the way you eliminate the bus number 4 completely and then you have 4 by 4 matrix and you by cron reduction you eliminate bus number 5. Okay?
Okay, thank you.
Okay. Any other question?
Yes, Doctor.
Yes, Abdulaziz.
What if the fault was in the middle of the line instead of at bus 4?
Well, this is a good question. This is a good question. What do you think, ya Shabab? Does anybody have a clue if the fault occurs at the middle of the line? And the fault occurs here at bus number 4, that's okay, خلاص, we know this. And if the fault occurs here at the middle of this line, what do you think? Now we have matrix Y555, Y plus matrix. And where is, how to proceed?
Doctor, I'm
Yes.
not sure.
Go ahead.
Sure, but it's just an idea. What if we add a bus instead of removing at the point of fault?
This is exactly the case. You have to add a bus at the fault location. And assume that and we have a fixture bus here. Since you in advance you know that this is the fault could occur at any point of this line. So let us add here, bus number 6. Bus number 6. And you can adjust, even you can make it, adjustable. You have here the impedance. You can write this is a factor X, and this is y minus X of the line or of the impedance times the impedance of the. So you can run your code or your stability study with different location by changing X from 0 to 1. Okay, and you multiply this by. So you can, the bottom line is that if the fault doesn't occur at the bus, which is exist here in the system, you have to create a fictitious bus at the fault location. And you can do the same. The procedure will be the same. And instead of having 5 bus, we have now 6 bus system. And the fault occurs at bus number 6. So again, we eliminate, if it is solid fault, we eliminate bus number 6 or row, and then we have this 4, 5, and again we will eliminate by Coulomb reduction the 4, 5 buses. We will proceed as usual. You just create a fictitious bus at the fault location. It is not necessarily the fault to be at the middle of the line. You can have the fault anywhere, and you can divide the ratio, and you can repeat your analysis. Is it clear, Abdulaziz?
Yes, thank you, Doctor.
Any other question? Okay, great. So,
Doctor, I have one question.
Okay, go ahead, Ahmed.
For the after fault period. So you said we remove the node 4, 5. Does this mean like we assign 0 to the admittance value for between 4 and 5 buses 4 and 5?
What do you mean?
In the solution, if you go to the post fault.
Post fault, so, part B. Okay, so this is the post fault. We remove line 4, 5. Then this line is stripped to clear the fault. Okay, it is no longer there.
Okay. Yeah.
So the first step is to modify Y bus matrix. Remove, in 520 how to do this. How to remove the line from Y bus matrix. Am I right?
Yes, Doctor.
Is it clear how to remove the line from Y bus matrix?
Yes.
And instead of forming the Y bus matrix from scratch, you can access, this is line 4, 5. So you can adjust, Y44, Y45, Y54, and Y55. So these elements needs to be adjusted if you remove line 4, 5. Is it clear?
Yes, Doctor.
طيب, okay, so this is Y bus. Again, خلاص احنا we adjust, but the matrix is still 5 by 5 matrix. The matrix is still 5 by 5. Again, you will add the loads at 4, 4, and 5, 5, and then you add XD prime for the machine, Y1, Y2, bus 1, bus 2, bus 3, and then you do Coulomb reduction. In this Coulomb reduction, you eliminate 4, 5. So again, as we have it here, so this Y bus matrix, you eliminate 4, 5 as such. If this is the solution number 1, if this is the solution A during the fault, This bus will be eliminated without coulomb reduction. You just remove it, and this also bus you just remove it during the fault. And this fault becomes now, this bus now becomes the reference. So you have, without coulomb reduction, you just eliminate bus number 4. So you have 4 by 4 matrix. And then you eliminate bus number 5 by coulomb reduction. And part B, this is the post fault. So we eliminate by coulomb reduction 4 and 5. After adjusting this Y bus matrix by eliminating removing the line. So, and then you can remove Y, the 4 and 5 by coulomb reduction. 4 and 5 by coulomb reduction. Okay. Did I answer your question, Ahmed? Or you still have?
Yes, doctor. We basically calculate the Y for 4 and Y for 5 for the admittance matrix. Then we do coulomb reduction. We calculate it again with the line removed. This is what I understood.
You adjust these. You adjust these entries of Y bus matrix when you remove the line 4, 5, and then you can, by coulomb reduction later you can do.
Okay, noted.
Okay, so
Doctor?
Yes.
I am afraid this kind of question in exam. How to go about this plenty? I hope something like this will not be in the exam.
Why?
Doctor,
Why? What is the difficulty if you have?
This is very complex, so one can easily get lost. So kind of. And if one makes one mistake, it will affect everything.
And it's not a problem if you did a mistake of the calculation, but you can see the steps 1, 2, 3. There is a systematic way to analyze the network, and these steps should be known. We have to start with load flow, and then you calculate the currents, and then you calculate the E prime, and then you calculate the Y bus of the load flow, and you adjust it to the loads, and to include the loads, include the reactance of the machines. And then by coulomb reduction, you eliminate all load buses. You keep only the generator buses. And then you can calculate VE 1, 2, 3, whatever number of the, and you can write the swing equation. So I hope the approach is clear. All the steps is clear. The sequence is clear. Forget about having a mistake, calculation mistake or something. This is not a big issue, but you have to know how to proceed for this. This is the major idea.
Thank you, Doctor.
Okay. Any other question?
Doctor, excuse me.
Yes, Doctor.
Yes. We have Ayub Al-Khalifa first, and then Ayub Al-Hurani, based on what I have here.
Sorry, Ayub. Doctor, I just wondering how we can calculate gamma, the angle we added in the equation.
Gamma comes directly from there.
So it will be given in the question, or
not given. It's not given. Gamma comes from here, from these angles, and you have here. Look, this is the equation here. This is the equation here. You substitute the theta 1j, theta 1, for example,
okay.
theta 1, 2, theta 1, 3. you have here theta 1, this is theta 1, okay?
Okay.
And theta 1, 2, 0. Magnitude is 0, angle is 0. Here is y13, this is the magnitude, and this is the angle. So gamma is calculated, and you are not having a constant gamma, and gamma comes from the network parameters. And this angle comes from the resistance and of the lines and so on, or the conductance of that you have it here. فthis gamma is calculated by product. Let us say by product you calculate gamma. When you substitute in this equation with delta 1, delta 1, 2, delta and so on, and you combine, then you end up with this equation. Is it clear?
Yes. So the gamma is the calculation for all the angles rather than, for example, delta 1 in the first case. I will make a summation for the all angle except delta 1. Then I will get gamma for PE1. Is it like this?
You do assumption?
No, not assumption. I will do a summation for all the angle.
When you do the summation, you end up with this.
Okay.
When you do the summation and you substitute with this angle, then you can have this cosine, sine, minus sine, cosine, and you can expand, and then you can have this. Okay?
Okay, clear. Thank you.
Okay. طيب الحوراني.
Excuse me, doctor, back to the, when we have the fault at the middle of the line, we added bus 6, but after that we deleted the column and row of 6. So, how the added row and column will play the role. We already we after that deleted them.
Okay, so you assume that the fault is a solid fault. Okay, and this is a special case. If the fault here occurs with an impedance, okay, the fault is the middle of the line, but we have a fault impedance here. So how to proceed? How to proceed?
Yeah, so if it's with impedance.
ما هو احنا بنتكلم عن general case. يعني generally speaking, لأنه actually when the fault occurs here, look, when we have a fictitious bus here, when you calculate Y44, you will not take all the admittance of the line. You will take only this part. And you can imagine that for this line, you have bus 4 and you have bus 5, and this is the situation here. Now, if we have a fault here, if this is a solid fault, during the fault, you can assume that this part of the line is just connected to the ground here, and this part of the line you just connected to the ground here. Okay? So when you form Y44, you add this part, not the complete line, and during the fault, I mean, and also during the fault, this will be Y55 equal to this, and you will add only this part of the line.
Yeah, clear, Doctor. The original Y bus will be modified. Yes. Okay.
So generally speaking, if you have fault at any point of the line, then you can create a fictitious bus here, and then you can proceed as usual.
Doctor?
Yes.
since we are connecting to ground, should we add this fictitious bus? Can we just proceed without it? If we consider it as admittances just added during the fault?
You can do this. And as I mentioned here, you can do this. You can say, no, during the fault, what I have, this point of the line will be connected to the reference, and this point of the line will be connected to the reference. So when during the fault, when I form Y bus matrix, I consider this part of the line here with this Y55, and I consider this part of the line with Y44. Okay? But this is a special case when we have a solid fault here. If we have a fault for an impedance, if you have single line to ground fault, in this case you have to use a fictitious bus clearly, explicitly in Y bus matrix, and then you can have Y 6 by 6 matrix. And you do the same.
Okay, noted.
Any other question? So we have a small quiz for 5 minutes. And I will make it now available. I'll make it available. So you can start right away the quiz. And in 5 minutes, we are talking about 6:33, we'll come back. So please start.
Doctor, I cannot see the quiz yet.
لا check what becomes available. في some people they are starting already. Check it again, refresh.
Still, I see just only 4 and 5.
والله, I don't know. I have now, but just refresh كده لأنه it's already it is clear available now for the students. I don't know why you experience such case. I just refresh or go and come back, log in again.
I make a refresh, but still it's not appear. Yes.
Who is talking?
I will just check now. 1 minute, because it's still not appear.
في ناس already خلصت
I will refresh again because it's still not. I have 4 and 5 only.
Should 4 and 5 should be 6. This is Q6. هو معروف بس معروف the round.
Still, Doctor, I cannot find it really. Quiz number 6.
الخليفة أيوب.
Yes.
والله it's very strange يا خليفة يعني انت ومعروف probably معروف is absent. But I don't know. Again, log in again. Go and log in again, or if you have link appears in the email or something, you can just check.
It will be in the assessment and test, right? Like the previous one.
The assessment and test stuff.
Exactly. But still, I can find only 4 and 5. I can send you a screenshot if you would like.
Okay. I don't know. يعني صراحة it is available and first time still go ahead and it should be okay. مش عارف أنا والله يا خليفة.
Well, even I looked out from the blackboard and then I looked in again, but still I can see 4 and 5 in there.
Can you share your screen, Masa, for example, to see what is going on there?
Okay. Can you see my screen?
No. I didn't see your screen.
Can you see it now?
No. You can't see your screen.
Now you can see it, right?
ده موبايل ده ولا ايه ده؟ ده موبايل؟
Yes, I looked out from my laptop and looked in the mobile, but still, as you can see, I make refresh, but still I see 4 and 5. You can see my screen, right?
Yeah, I see, but this is mobile.
So,
يعني
even the laptop I can't.
أخش
As I
من
go
على
to the
اللابتوب
course
كده.
and the assessment, and I find only 4 and 5.
Assessment tests.
Yes, and I make also refresh, as you can see, but it's still not appear.
طب ارجع تاني كده، ارجع تاني لو سمحت. Go back. Where is the assessment tests?
Here in the course content, then I will have here assessment and test. Then I have 4 and 5 only.
I don't know.
Doctor, I think he can try to use the browser. He can try to use a browser.
Another browser?
But sometimes the application of Blackboard have some delay.